Hi everyone! Today let's talk about section 4.5, Chebyshev's theorem. Chebyshev's theorem: x is a random variable with mean mu and variance sigma squared. Then for all k positive, the probability of the distance between the random variable x and mu is greater or equal to k sigma. The probability of this is less than or equal to 1 over k squared. What does this represent? So do you still remember mean represents the center of the probability mass? So if we draw the picture, let's say our probability looks like this. Okay, and mu is like the center of the probability mass. Then we know the probability of the random variable x near mu. The probability of x near mu is large, and the probability of x far away from the mean is small. So usually if we say k is a large number, then k sigma, this is a large number. So the probability of the distance between x and mu is large. So this means if the probability of x far away from the mean is less than or equal to 1 over k squared. So 1 over k squared is going to be a small number. So this means probability of x far away from the mean is very small. Okay, and this is the same as saying the probability of, so the distance is greater or equal to k sigma. So it means either x minus mu is less than or equal to minus k sigma, or x minus mu is greater or equal to k sigma. So this probability is less than or equal to 1 over k squared. On the other hand, if we want to compute the complement, well, the complement of this is the probability of x minus mu less than k sigma. Okay, and then this guy will be greater or equal to 1 minus 1 over k squared. So this is the complement. And this is the same as saying the probability of x minus mu is bounded between minus k sigma and k sigma. So this probability is greater or equal to 1 minus 1 over k squared. Okay, we can also add mu to the inequality. Then we get mu minus k sigma less than x less than mu plus k sigma. The probability is greater or equal to 1 or minus 1 over k squared. What does this mean? So let's say this is the mean, mu, okay? And let's say here, this is mean, mu minus k sigma. Let's say this distance is k sigma. And let's say this distance is k sigma. Then this guy is mu plus k sigma. So it means the probability of x lying in this range is big. The probability is big. How big? Bigger or equal to 1 minus 1 over k squared. So when k goes to infinity, 1 over k squared close to 1, right? So this means the probability of x near the mean is big. Okay, kind of makes sense, right? The probability of x near the mean is big. See, we have big probability. And the probability of x far away from the mean is very small. Okay, so it kind of makes sense from the picture. Okay, what is the proof? Alright, so let me show you the proof right here. And the good thing about this Chebyshev's theorem is we don't know what is the random variable. It could be a binomial distribution or geometric distribution or hypergeometric distribution. It could be any random variable. Okay, we don't need to know which distribution it is, but we can still have a bound for the probability. Okay, so proof. So if you can remember, variance equals sum of x minus mu squared times the probability of x equals x. Alright, now this x is over the range of x, right? It's like all the real numbers. Okay, and now I'm gonna separate this real number into 3 regions. Okay, let's call this be R2, and let's call this be R1. Let's call this be R3. Okay, so x in R, now we can separate the sum to be x in R1 of x minus mu squared p x equals x plus sum, the x is in R2, and we have x minus mu squared p x equals x plus sum x in R3, region 3. And then we still have the same things inside the sum. Okay, so now, what happened? Okay, now so this guy is greater or equal to, so we have 3 terms, right? If we just consider 2 terms, these 2 terms, then we have this guy is greater or equal to the 2 terms, right? Because the inner part, this is positive, right? So if we count smaller x values, less x values, then we get greater or equal to, we just look at the sum over the region R1 and R3. So x in R3 right? Okay, now what happened? So for x's in R1 or R3, what is special about it? Well, you can see if x is in R1 or R3, what's the distance between x and mu? The distance between x and mu will be greater or equal to k sigma, right? So that's why x minus mu squared will be greater or equal to k squared sigma squared. So that's why we start with sigma squared, and this guy is greater or equal to on the region R1 and R3, we get so this region x is in R1 or R3, and x minus mu squared is greater or equal to k squared sigma squared, and then we have the probability x equals x. And then what do we get now? So because k squared sigma squared, they are constants, so we can put it outside of the sum. Now, alright, so this is what we get. Now, if we divided both sides by k squared sigma squared, then we get the sum, x is in region 1 or region 3, probability, this is greater or equal to 1 over k squared. Sorry, let's see. Oh, less than equal. Because this is on the right hand side. It's less than equal to the left hand side. Okay, so we get less than equal. And on the left, well, that is exactly the probability of x minus mu greater or equal to k sigma. Okay, now we have shown the theorem. This is the Chebyshev theorem. Let's see how we apply the Chebyshev theorems in our examples. So example 1, the number of customers visit a car dealer's showroom on a Saturday morning is the random variable with mean mu is 18 and sigma, the standard deviation, is 2.5. Find the probability 8 less than x less than 28. So what you do is you're gonna draw the picture. keep in mind the mean mu is always in the middle, and then on the left we have mean mu minus k sigma. On the right we have mean mu plus k sigma. Okay, now we want to find x's between 8 and 28. Okay, so and the mean, what is the mean? The mean is 18. Okay, so using this, you can see what is k sigma. What's the distance between 18 and 8? That is 10. And also on this hand, you can also see k sigma is 10. And furthermore, k sigma is 10. So what is k? 10 over sigma. The sigma is 2.5. 10 over 2.5 is 4. So by the Chebyshev theorem, we have the probability of x between 8 and 28. So we know the probability of x near the mean. So this is near the mean is large. How large? Greater or equal to 1 minus 1 over k squared. Okay, so remember that the two version, x far away from the mean, the probability is small. How small? Less than or equal to 1 over k squared. And the probability of x near the mean is big. How big? Bigger or equal to 1 minus 1 over k squared. Okay, so that's why here 1 minus 1 over k is 4. So 4 squared is 16. So this is 15 over 16. Okay? So now we can get a bound for this probability. And in this problem, we don't know what kinds of the distribution. We don't know whether it's a binomial distribution, hypergeometric distribution, or geometric distribution, or any other kind of distributions that we haven't learned. So we don't need to know what kind of distribution, but we can still use the Chebyshev theorem as long as we know the mean mu and the standard deviation sigma. Okay, so we mark. So in this problem, we don't know what kinds of distribution. Okay, so in this case, use Chebyshev's theorem. If we know mean mu and standard deviation sigma. Okay, and the weakness is, you can see we only get a bound, so we only get a bound. We're not getting exactly the probability. Okay, so this is the weakness, not the exact value of the probability. Alright, let's continue on example 2. Flip a fair coin 40,000 times. Show that the probability is at least 0.99 that the proportions of heads will fall between 0.475 and 0.525. Okay, so flip a fair coin 40,000 times. This is a binomial distribution. Okay, well, didn't we just said for the Chebyshev theorem, we don't need to know the kinds of the distribution? Yeah, we don't need to know it, but if we know it is the kind of the distribution, we can use this information to find the mean and standard deviation. Okay, and in this problem, you see we flip the coin 40,000 times, so n is 40,000. And this number is so big. Do you still remember how do we compute the binomial distribution? We either use the PMF, which is the formula, right? And choose R and then number of success, so P to the R times the number of failures, so 1 minus P to the N minus R. So this is the formula for the PMF. And it's better to use the CDF to calculate because we can just find the value in the table and then just subtract the two values. But remember, in our table, the n is only up to 20. And in this problem, it's 40,000, which is a lot. So it's really hard to compute the formula. No matter the CDF or the PMF, it's hard to calculate. Think about 40,000, choose any number is already so big. Okay. So let's continue. So show the probability is at least 0.99. The proportion, okay. So we want to know. So let x the number of heads, right? So x is the number of heads. So this problem is say the proportion of the heads will fall between 0.475. So n is 40,000 times the proportion 0.475 less than x less than the and 40,000 times the proportion is 0.525. The probability of this is at least 0.99. So we want to show this. Okay, and this is the natural format of the Chebyshev theorem. Okay, now let's check it out. Because we have the binomial distribution and it is a fair coin, so P is 1/2. And if you can remember what is the mean for the binomial distribution, n times P. So 40,000 times 1/2 is 20,000. And then how about variance? So variance is n times P times 1 minus P. So we get, and we know NP is 20,000. 1 minus P, 1 minus 1/2 is still 1/2. So we get 10,000. And sigma is the standard deviation, which is the square root of the variance. Square root of 10,000 is 100. Nice number, right? So let's draw a picture. So when you use the Chebyshev theorem, I strongly recommend you to draw the picture. Remember, mu is in the middle, and then we have mu minus k sigma, mu plus k sigma. In this example, mu is 20,000, right? And then on the left bound is 40,000 times 0.475. And what is that? 40,000 times 0.475 is 19,000. So this is 19,000. And then we have 40,000 times 0.525 is 21,000. So 21,000. Okay, what's the distance? It's 1,000, right? The distance 1,000, and 1,000 is k sigma, and you will see this is 1,000, this is 1,000. They're the same, right? Okay, so k sigma is 1,000, and we already know sigma is 100. So k equals 1,000 over sigma, which is 1,000 over 100, which is 10. Okay, then we know by the Chebyshev theorem, we know the probability of x near the mean. Then how near? So it's 19,000 between 19,000 and 21,000. This probability is large. How large? Greater or equal to 1 minus 1 over k squared. And k is 10. So k squared is 100. Well, 1 over 100 is 0.1. 1 minus 0.01. Sorry, 1 over 100 is 0.01. So 1 minus 0.01 is 0.99. And see, this is what the questions ask us to verify. So we just show that the probability is at least 19.99. That's the proportion of the heads will fall between 0.475 and 0.525. Okay, so and you can see when it means when n is so large, the proportion of heads is close to you can see the mean is 20,000, right? 20,000 is the mean. It's like we have 40,000 times we flip the coins 40,000 times, and 20,000 times we can get head. So because it's a fair coin, so the probability of getting head is 1/2. So that's why 50% of the time we can get head. Okay. So far so good, everyone. So in this example, you can see sometimes the problem might give us the kinds of the distribution. Then we can use this information to figure out the mean and standard deviation. And once we get the mean and standard deviation, we can use the Chebyshev theorem to find bounds for the probability. Okay, so probability of x near the mean is large. How large? Greater or equal to 1 minus 1 over k squared. And the probability of x far away from the mean is small. How small? Less than or equal to 1 over k squared. Okay, so those two concepts, so keep in mind. Okay, so this is session 4.5. And if you have questions, feel free to ask me. Bye!